Okay, so let's get started with some introductory comments. So in the last 50 years or so, we almost always discovered what we expected based on indirect evidences. Now, let me give some examples. Gym mechanism, for example. This told us about the existence of charm quark around a GeV, and finally we discovered charm quark around a GeV. This lack of unitarity from Fermi theory told us about new states around 100 GeV, and that's what we discovered in the form of W and Z bosons. CP violation told us about the existence of third generation. We finally discovered third generation. Then precision flavor physics, for example, B2S gamma, and electric field told us roughly about top quark mass, and precision electric field finally told us about Higgs mass. And in all these cases, we had indirect evidences which told us about the existence of new physics, where to look at, for example, in terms of masses of quarks and Higgs and so on. Unfortunately, we now are left with mostly arguments only. For example, we have hierarchy or naturalness problem or scale separation, whatever you want to call it. We have WIMP miracle, gauge coupling unifications, and so on. And more importantly, at least starting from the WIMP miracle and below, we always have a UV solution. And by UV solution, I mean that it's not necessary to have any light states in the spectrum. You might argue that that may be also true for the hierarchy problem, but that's, I think, debatable. So I think that we need more indirect evidences now to make progress, to make definitive progress. And that's what we are missing currently. So let's start talking about supersymmetry. And to set the stage, let's see what indirect evidences or lack of indirect evidences we have now. In this figure, I saw the scale of new physics, which is constrained from delta F equal to 2 observables. For example, BB bar mixing, KK bar mixing, DD bar mixing, and so on, for some specific new physics scenarios. The different colors are the different constraints coming from different meson anti-meson system. For example, the green is from K, mostly CP violation from in K system, YOLO is from D systems, and so on. And the different numbers C1, C2 to C5, they correspond to the different operators you can write down for these mixings. Just to tell you, the operator 1 is exactly has exactly the same chiral structure as the operator of the standard model. However, operator 2 to 5, they are chirality violating, so they mix left and right chiral fields. If you want to know more details about how these why some bounds are stronger than some other bounds, then it's good to remember that the CP violation in K systems are extremely suppressed, and that's why the bounds are dominated by them. And there are the bounds are stronger for the operator C2 to C5 because the chirality violating operators are enhanced by RG effects and also by matrix elements. For those who work on left-right symmetric models, you might remember that in left-right symmetric models, these chirality LR operators are generated, and that's why the scale was severely constrained from KK bar mixing. Now I have to tell you how these bounds are obtained. These bounds are obtained assuming that the flavor violation has the standard model part, which I denote by CSM time OSM, plus CS nu P, NP, which is C new physics at the scale lambda times O new physics. And C new physics is parameterized by two coefficients called F and L, where F carries information about the new physics couplings and L carries information about the loop factor. Now, in these bounds, F and L both of order 1 have been assumed, this means that we're assuming that new physics is strongly interacting and has arbitrary flavor structure. These bounds are very frustrating. As you can see that these bounds tell us that the new physics scale has to be extremely high of order 10 to the power 4 to 10 to the power 5. So there's a question. Okay, sorry. Now, but one can do better in the sense that we can actually change this assumption of F of order 1 and say that F is similar to FSM, where FSM is the CKM factor of the relevant standard model amplitude. In that case, you can see that the new physics scale is the bound on the new physics scale now is much weaker, and from 10 to the power 4 to 10 to the power 5, we go to around 10 TeV to 100 TeV. This assumption of F has the same flavor structure at F standard model is often known as the next to minimal flavor violation in the literature. But still, it's not great because the scale is still extremely high. In particular, for operators C2 to C5, which has a different chiral structure than the standard model. So what we can say, or we can assume that and if the new physics had the same chiral structure as a standard model, in that case the bound will be much weaker and goes below roughly 10 TeV or so, and that is what is shown in the first set of bars, vertical bars in C1, because C1 has the same chiral structure as the standard model. In the literature, this is often known as minimal flavor violation. And on top of this, if you assume that there is a loop factor, the bound can go much below, and you can allow new physics at the TeV scale. And this is why in supersymmetry, for example, we were okay to consider particles at the TeV scale and still be consistent with the flavor observables. Now let's see how it works out in supersymmetry. In supersymmetry, as most of you know, the flavor violation in principle can happen because of the existence of the soft mass terms and the A terms, the trilinear terms. But in MAB supersymmetry, we write them in powers of the Yukawa coupling in the way I have shown in this slide. And now remember that with this assumption, we are assuming that the Yukawa couplings are fundamental. So the flavor structure is completely given by the Yukawa coupling. The flavor structure of the new physics models is also completely given by the Yukawa coupling. So we are not explaining why the Yukawas are the way they are. We are just saying that the Yukawas are fundamental. Often a simplifying assumption is made, which is phenomenologically driven, where we set all the BI coefficients to 0. However, this hypothesis is not renormalization group invariant. So what happens is that you have to set it to at some high scale, and then RG evolutions will generate them at the infrared. In this case, we'll get effects which are of order a loop factor 1 by 4 pi square times the logarithmic of the ratio of square of the cutoff lambda to the mass of the superpartners. This leads to quite sizable effect in particular high scale models like supergravity, where lambda is usually identified as close to the Planck's mass. However, the situation improves in models with gauge mediated supersymmetry breaking, since the scale lambda is identified with the mass of hypothetical messenger scales, and this mass scale is arbitrary and it can be low enough to reduce the effect. However, even in this case, you can interestingly get quite large effect because supersymmetry parameter space is quite complicated. And here in particular, in the large tan beta regime, you can get quite a significant effect, as many of us know who worked on supersymmetric phenomenology. And let's understand how this happens. So you all know that in supersymmetry, at the tree level, because of the holomorphy of supersymmetry, the down type quark masses are completely, the down type quarks coupled to the down type Higgs, and up type quarks are coupled to up type Higgs. However, once supersymmetry is broken, you get the second term, which I have written in L effective, which has HU star. Now, in the presence of these two terms, you see that there are two different matrices. One is YD and another is YD times whatever is given in the square bracket. And you can't simultaneously in general diagonalize these two matrices. So you will have additional Flavour violation beyond what happens due to CKM. If you were worried about how at one loop this term YG, epsilon G and epsilon U can be generated, the diagrams are there. You see that these diagrams are proportional to tan beta by 16 pi square. So this is 1 by 16 pi square is coming from a loop effect, and tan beta is coming because if you replace HU roughly by HD times tan beta, you see that compared to the first term, the second term is tan beta enhanced. So in the large tan beta limit, you can remove the loop suppression quite efficiently. And this led to very exciting possibilities of large enhancement in BS2 mu mu, for example, which is now completely ruled out by data. So this is just to tell you that supersymmetry, even in the MAB framework, allowed the possibility of large enhancement in the large tan beta regime, however, which is ruled out by data. Am I audible?
Yes, you are.
You are audible. You are audible.
Okay. And how much time do I have?
So if you can finish in 15 minutes, it will be very good.
Okay. So what have we learned? You see, there's nothing new in whatever I have told you in the last roughly 10 minutes. But what we have learned is that
Diptimoy, somehow
yes.
I'm not able to see this. I'm able to see you, but not the top screen, the slides.
Slide is moving. I can see the slide moving.
Oh yeah, no, because I can see Diptimoy in a much bigger size.
No, that because you clicked on Diptimoy's photo. So if you do the other way, you click on the other window, you will get Diptimoy being smaller and the slide to be larger.
Okay, thanks.
Is that fine now?
Yeah, now it's fine. Thanks.
Okay. So what did we learn from this very painful exercise? We learned that the flavor structure of supersymmetry must be MAB-like. None of the statements I'm going to write here is a theorem, but it's a kind of a guidance. It's preferred to have a low mediation scale because then you reduce the RG effect. It's preferred to have low tan beta. And given the LHC imposed relatively high scale of mass scale for the super partners, large effects are now ruled out within the context of supersymmetry. So we should keep increasing the precision and hope to see small effects. Now, if you are worried about the possible maybe pessimistic future and ask why we should just keep increasing precision, then I should remind you that the fact that indirect CP violation in the Kaon system was of order 10-3, and if we had abandoned searching for physics even at the beyond at the level of 1%, the history of particle physics probably would have been completely different. So precision measurements are important, and in my opinion, at the moment, that is the only way to proceed. Of course, that doesn't mean that we should not do direct searches. We should definitely do, but as I have told you, that the reach of precision physics is much better than direct searches. In direct searches, we can probably only go to roughly a few TVs to 10 TV in the next 10 years or so. Okay, now in the last 10 minutes or so, let me talk about more recent and maybe exciting results in B decays. So let me start with RD and RD star because that is theoretically simpler. The experimental result has been summarized by the previous speaker, so I won't bore you with the same information again, but I'll just tell you that the RD experiment by RD SM is roughly 1.1, and that is also true for D star. Gagan had mentioned about the issue of these results being mostly dominated by the oldest Babar result, Babar 12, but whether one should take average or take the latest result as a matter of debate. I'm not going to talk about that now. I'll just assume that there is this deviation and how what supersymmetry tells us about it. You see that roughly there's 10% deviation from a tree level standard model process. And this is huge. 10% of standard model tree level is extremely huge, and that's what makes our life very difficult. This tells us also that loop level explanation of this anomaly is very difficult, because if you want to explain 10% of standard model tree level by a loop, then you have to put the new particles in the loop to be extremely light. So all explanations are tree explanations. And let's see how supersymmetry does in terms of explaining RD and RD star. The first thing which comes in our mind is H plus the charged Higgs, but I think it's known for a long time that the charged Higgs contribution goes in the wrong direction. So instead of increasing RD star compared to the standard model, it actually ends up decreasing it, and that's why charge Higgs is not an explanation. In the context of RPV supersymmetry, you can do by a right-handed bottom. You see that this is a leptoquark-like, the couplings are leptoquark-like couplings, and you can explain with roughly a TeV's bottom and offered a 1 lambda prime coupling. This was first pointed out by Deshpande and collaborators. This situation is not ruled out by direct searches. However, you see that unless you want extremely large values of lambda prime, it can be ruled out in a few years time. Since this conference is about the reach of high luminosity LHC, I should also show what high luminosity LHC can tell us about this decay. And you can see in this figure, which has a projection for the uncertainties of measurements of RD and RD star for different integrated luminosities for LHCb at 23 femto1 inverse, 50 femto1 inverse, and 300 femto1 inverse. And you see that the uncertainties will reduce a lot in the next decade. And so in any case, independent of whether we trust the Babar result or we trust only the LHCb results now, I think this issue will be settled in the next 10 years or so. Now let's talk about RK and RK star, which was described as the poster child of new physics searches by Gagan. So RK now is very exciting because we have this new exciting result, and which tells us that we have a significance which is of order 3 sigma. For RK star, the situation is slightly less exciting because the deviation is still at the level of 2 to 2.5 sigma. Remember that in the standard model, this is the loop effect. this is in the EFT language, this is due to mostly two operators, O9 and O10. In standard model also due to O7, but in the new physics context, only these two operators O10 and O9 are important. The Wilson coefficients of these operators are of order 4 in the standard model, and if you want to explain it in new physics, you need of order 0.4 in new physics. So that means again you need roughly 10% of new physics. However, the good news is that here the new standard model is loop level. So you need 10% of standard model, like what we had for RDSR also, but here is 10% of standard model loop, and that allows heavier scales. Let's see whether in MSSM you can do it. In principle, yes. However, the only way to get lepton non-universality is to assume that muons are effect in mu mode and not in electrons, is to assume that muons are light of 100 GeV and selectrons are decoupled. We have to assume winos to be also light, and bottoms and strange quarks are also light, and is below 500 GeV or so. However, as all of you know, this is completely ruled out by direct searches, and so MSSM actually can't explain RK star. This is also, even without these details, is easy to understand, because the loops in MSSM are some coupling to the power, some positive power 2, 3 by 4 pi square is like standard model, because the couplings are like standard model couplings, the magnitudes are like standard model couplings, like gauge couplings and so on. So you can understand that if you want to do it by loops and assume couplings which are off order of standard model couplings, you need also particles which have masses off order of standard model, and that's completely ruled out, and so you don't do it in MSSM, in RPV R parity conserving MSSM. Let's see whether you can do it in RPV supersymmetry. Here you can. There are many diagrams. I've given only 2 examples where there's this neutrino and we know in the loop, and in the second case there are only neutrinos in the loop in terms of new particles. The generic feature of these explanations is that unless you have masses which are very low, which are anyway ruled out by experiments. So for example, if you have masses of order TeV at least, then the couplings have to be large, which is shown by the red shade in the figure on the right. Moreover, all explanations are quite ad hoc in the sense that it does not tell us more about UV physics or the Flavour structure. So in the context of RPV supersymmetry, indeed, we can explain, these are existent proofs that you can explain with phenomenologically acceptable values of couplings and masses, but they don't teach us much about UV physics or Flavour structure of the underlying UV physics. Again, since we are talking about high luminosity LHC, I should mention that the improvement which is expected in the LHCb upgrade 1 and upgrade 2 is extremely huge. These numbers are slightly old from 2018. That's why the 9 Fem/1 inverse is still a projection. As we know that 9 Fem/1 inverse results are available for RK at least, but this tells us that how much improvement we can get in the next 1 decade or so. So independent of whether these anomalies or deviations survive or not, will have much better idea about whether new physics exists in these modes or not, and which in turn can be used to get information about physics beyond the standard model. The only final comment I'd like to make is that we should keep looking for indirect evidences for physics. beyond the standard model through precision measurements, in particular in the flavor sector, because flavor has the potential to probe physics at a very high scale. And then on a much lighter note, you should, the organizers should also keep organizing such conferences, maybe in offline mode, to discuss and get new ideas. Thank you.
Shubhavati, shall I go ahead?
Shubhavati?
It's probably muted.
I think she asked me to unmute.
Sorry.
Oh,
Yeah, Seema, you asked your question. Sorry. Yeah.
Thanks, Diptimoy, for a nice talk. So I had a question on your slide where you were mentioning RD star and the charge Higgs context. I don't know the slide number because those were not
Yeah,
mentioned
because
in
the
slides.
number was
Just a
not
minute.
there. I also tried to know that.
Yeah, I think next one. Yeah, you said
Yeah.
something that the value, the charge Higgs contribution will put the RD in different way than what is expected. Why
Yes.
did you say so? I mean, I somehow lost there.
No, this no, I did not explain why that is true. It turns out that if you compute this ratio RD experiment by RD SM in the standard model, you get a form which is 1 minus some function of masses which is positive. So that means if you now have non-trivial effect from charged Higgs, it will only reduce this ratio below 1. However, what we need to explain the anomaly is to make this ratio more than 1. So it goes in the wrong direction.
So is there a quick answer to it, that why it happens this way? Because of the Higgs charge Higgs component, the contribution?
Why this just a matter of what the couplings are in the charged Higgs vortex.
So then, Diptimoy, just to continue or sort of get a finer answer, understanding of what Seema is asking, that is why for your in your plot, the values of the lambda primes are negative. I mean, there you have, for RPV, you have no constraint on whether it should be positive or negative. So you can actually, is that what helps the RPV explanations?
Yeah. So in our
that you have no control, you have more control.
So first, there's a qualitative difference also between this bottom explanation and charged Higgs. You see, charged Higgs is not a leptoscalar, leptoquark-like explanation. So it's CB, and the bottom is a leptoquark-like explanation, which for other reasons is better. And then, as you said, that the couplings are much less constrained in RPV, which is not the case for charged Higgs. The charges are completely dictated by the masses.
That's why I said gauge couplings and the masses decide.
Yeah. Gauge couplings and
the signs are positive. Here you can play with the signs also.
Yeah. Here I can play with this.
I guess that is part of the answer to Seema's question.
Okay.
But Shubhavrati, may I please go on, because it's very much related actually. So on this same slide that you are showing just now, Diptimoy, when you were speaking, you said something about large size of lambda primes will be required. So if as the limit on the B2 starts going up, so how large do you need the lambda primes?
Now offered a TV bottom quark, you
require 1.
You will roughly offer a 1. So now you see
when do you rule out, when do you reach the unitarity limit?
Unitarity, okay. So unitarity, it depends what you mean by. So if it is just a normal tree level unitarity limit, then it's just a loop expansion parameter. Then you can go probably up to root of 4 pi. So let's offer a 3
that's
or so.
really the sense in which I wanted to get.
Yeah, so it's about 3 or so. But as you know that if you now start analyzing things in more details, you'll usually get always a much better bound. And so you see, we shouldn't go beyond of order 1 or maybe 2, but so that is a rough picture.
Okay, that's the answer. And the second question I had was for this neutrino masses. You had next slide, I think. Here. So what I wanted to know is that what are the limits on neutrinos that can be probed at the LHC?
So first, see,
and it will be only in the RPV scenarios, basically. There they can be tested effectively.
Yeah. So one thing is neutrinos are also related by SU. These are left-handed neutrinos to leptons.
Yes.
So indirectly, various limits which apply to lepton masses will also apply to neutrinos.
I know, but they are not somewhere around 1000. Okay, that is why I said this.
So it depends on which coupling. It depends on various details, but typically the bound is of order TeV. Even now.
Even now, this neutrino mass limit is of the order TeV.
Yes, order TeV.
With the lepton limits of 300 GeV.
Leptons. No, what did you say?
Leptons are 300, 400 GeV.
You see, this depends on. You are saying the completely model independent.
With your SU2 argument. And the charged lepton, this neutrino that would be allowed would be lightish, no? And you can only probe it in the RPV really effectively directly if you want to probe neutrino. Your best bet is only RPV searches.
Why you can't do it in?
How do you do it?
No, even if you assume neutrino mass related to the lepton mass, then you can do in normal MSSM also, right?
No, but that is what I said, that the lepton searches, that you can only translate the lepton
I see. Now I understand. Okay. Now I understand. Oh, yes, you are right. So if in normal MSSM you want to get a bound on neutrinos by relating it to
that's a rather low limit. That's all I know.
So that is rather low. However, now there are bounds in the RPV context in the presence of this lambda and lambda prime coupling.
That only in the RPV scenario.
Okay. So I misunderstood.
Probe this neutrino, and there I didn't know the current limits.
Yeah. So there for off order 1. So off order 1, like coupling, the bounds is already a TVs.
Okay, good.
Below
so
TeV,
that means that the region that is there at the top of your scale is just about allowed, is it?
Yeah, actually slightly it is allowed, but only in a very let's say optimistic scenario.
And then if I want to look at HL-LHC, what region can I probe?
So in HL-LHC, from direct searches, you will improve the bound by maybe factor of 2 conservatively.
So on this plot, it might be nice if you show a limit that HL-LHC can probe.
So that's what I'm telling you. So HL-LHC in CMS and ATLAS, there the luminosity will, let's say, go by a factor of 10. And so that roughly corresponds to a factor of maximum 2 to 3 in terms of masses, roughly.
Okay, thank you.
So from 1 TeV, you go to 2 to 3 TeV, and there you see that you will need very large couplings.
Okay.
Seema, maybe you can ask your question to Gagan.
Yeah, it's a quick one. So Gagan, thanks a lot for the nice review. You made a comment about the LHCb luminosity of 1 femtobarn inverse being equivalent to 1 attobarn for the Bell one.
Correct.
How do we get that? I mean, this was an interesting one, which I have been ignorant about.
Seema, good question. Right. Actually, I gave this question to my student. So it is the cross section, Seema. So the PP going to BB bar, I mean, B and whatever measure, and then you look at the large eta the coverage that I said, no, the forward, backward. Ideally speaking, you should have 2 spectrometer, but okay, half of that is as good as you can get. And yeah, so it is the cross section basically. Is the
so it's basically the forward PDFs, that contribution and versus whatever we are getting.
Absolutely, absolutely.
But then Gagan, I have a question. Second question, continuation of Seema's. I and Seema seem to be playing a duet.
Okay.
Now the question I have, Gagan, is this basically is just on cross sections. So the abilities of the different experiments to look at things is not folded
efficiency. No. So the efficiency. Okay. Right. So obviously the efficiency. I mean, what you are saying is the efficiency, right? I mean,
exactly.
So the point is, I'll come to that. So the point is, Bell 2 is as like CMS or Atlas is almost close to 4 pi. Actually, it's a little bit asymmetric in terms of because there is asymmetric collision. On the other hand, LHCb is all forward direction. Yeah. But the fact is, you have the cross section. I mean, most of the particles are in the forward direction. So the acceptance wise, obviously they lose, right? And then particularly if you have a very low momentum track, I mean, so that's not something LHCb can do very efficiently. So obviously the efficiency wise, Bell 2 profits on if you compare to LHCb.
Yeah, but is that been included in your
but that will not change it by order of I mean, at best you know that how much it will go down to. So maximum is 100%, 10%, right? I mean, what I'm trying to say, efficiency cannot take it like several order of magnitude.
No. I wanted to see whether LHCb will be worse off. That is why I asked this question.
Yeah, LHCb, you pick up any particular channel.
Whether the efficiency factors will make it worse for LHCb.
Slightly worse for LHCb. That is correct.
That is really what I wanted to see. How much?
That is
particularly true. Because LHCb
let me give you a number. Small. Let me give you a number. For the Bell 2, if I'm talking of B2, K star, mu, K star, EE, they have a similar efficiency. And the efficiency is close to 30%, 20 to 30, I mean, 25 to 30%. That's the number what you're talking about. For LHCb, it will be like almost half or something like that. Yeah.
Okay. So it's a factor 2. Okay.
Factor 2. But in this spirit of what I said, there.
No, that's okay. I wanted to see, because by and large, LHCb is such a strange detector that sometimes the feeling, the sort of order of magnitude ideas that one has in mind can actually go wrong for LHCb. That's why I asked this question.
Sure.
So, because 4 pi, as you correctly said, 4 pi detectors and LHCb are different stories. So back of the envelope estimates sometimes can go quite wrong. And hence I asked this question. Thank you.
Yeah. So just a question. Sorry, I think we should go for lunch.
Yeah, but one quick question I have.
Before you ask. So like this is a comparison. Of course, charge Higgs part doesn't come in correct. I mean, the way I understand, and obviously that is what I was trying to actually respond to Seema also. So now the way I understand, if you have leptoquark model, like particularly this various kind of leptoquark, vector leptoquark, scalar, and various way, the way I will also add this G-2 of the muon. I mean, we had the discussion, and then you put all the anomaly together, and then you want to say what is the best possible model, whether it is leptoquark or it is your favorite or our favorite RPV violating SUSY. So I mean, because SUSY you said there's a trouble for the RK star, and then you have to go to some crazy thing.
No, I said in R parity conserving SUSY you can't do RK
it doesn't work. Right.
So if you go to R parity violating SUSY, you can do it.
Yeah. So my question is, you put all the anomaly together, including G-2, and then tell us that which is the on the theory side.
Okay, that exercise I have not done, but I'll tell you what my guess is.
It will be interesting.
In general, simplified leptoquark models will win. I'll tell you why. Because you see, in the RK star explanation, the RK star in the standard model is loop. So if you can do it in the at tree level in the new physics, then you can allow heavier masses. Now, but you see that in my okay, where is so in my thing that this was not by tree level. Now in general, there is a tree level diagram which gives rise to B2SLL. Also in RPV SUSY, this is mediated by stop. However, this gives a wrong chirality, the wrong chirality operator. So just that does not work. So that's why you have to do this at the loop level. Now, once you do it at the loop level in RPV SUSY, necessarily the mass scale goes down. So in the RPV SUSY context, you do you have masses which are relatively low. So that's why you, in some sense, is good because you can discover the masses. But in some sense is bad because then you also constrain it more because the masses are low. So now if you do a feed to all the data, because leptoquark simplified model has much less restrictions because it's simplified, it's not part of a grand structure like supersymmetry, that will win because you can tune various things in the way you want. So that is a guess.
Okay. Sorry, okay, Seema, I interrupted you. You have anything? Otherwise, you.
No. Yeah, Seema. Last question from Seema. Seema, you unmute.
Yeah. So that was for Gagan. That are there any scenarios where LHCb will be much quicker in getting to the conclusion than the Bell?
See, the problem,
I mean,
Seema,
in terms of like luminosity, that's the reason I asked.
No, it's the question of one is luminosity, but imagine the scenario, ATLAS getting the Higgs and CMS doesn't get the Higgs. Would you have trusted the Higgs? So it is very, very important. I mean, obviously, I don't have to tell
ATLAS
you.
and CMS are comparable. Here, the luminosities you're talking about is a factor of 3, means magnitude of 3.
So the key thing is the electron part. I mean, if you ask Tuhin Roy, I don't see him in the audience. Tuhin has very strong reservation about the RK star, saying LHCb, well, the electron is crazy. How much trust I will do and things like that. I mean, okay, so that is so what I'm trying to say. You know, they will get a much precise result, like let's say with a higher luminosity, if this anomaly stays there. I mean, if it is a real thing, they will get. But the electron, given the complexity in the electron, even if with their upgrade where they want to put certain detector in very close to the magnet, so they have a dipole magnet. So as Rohini said, LHCb is really a strange detector. They have, for the first time, you have the tracker, so-called the vortex locator inside the beam pipe. Can you imagine? So it is like they have a robot. So I thought, you know, I just want to tell you all, I mean, probably all of you know. So before when they collide proton, so the robot takes out, I mean, before that, the velo detector is like this. And once there is a stable beam and things are all fine, they take it now back inside the beam pipe, okay? Inside the beam pipe. And the other thing about, they have a dipole magnet, which you don't have in CMS or ATLAS. And so they will have some detector, even the magnet, on top of the magnet, some kind of crazy thing they're doing to improve on this electron thing. The kind of plot I saw that you see on the lower side, there is this peaking background, so-called, to control that. So hopefully they will be successful.
So naively speaking, limited by the purity and the precision.
Yes, exactly.
Okay.
Exactly. So and it will be obviously very important to have an independent cross-check for a substantially lower energy experiment, completely different setup, and that is where the key lies in the build.
Yeah, I mean, the reason I asked is essentially if we have one hint, then the other experiment can tune accordingly and try to see or focus on some particular point. That's what. But yes, thank you, Diptimoy and Gagan. Difficult to get both of you together, and otherwise also.
Hey, we are both of us within 150 kilometers of you. What do you mean by difficult to get both of us?
Okay.
You have to make us travel. I go to Pune every week almost.
We can have a private Skype. We can
settle it in Pune.
Okay, I think we should wait for lunch maybe.
I would like to thank all the speakers for very nice talks. We generated so much nice discussions also.